Now, let's move on to the next part. It's about the change in internal energy and enthalpy change. Now, in chemical reactions, it involves temperature change. If the reaction is exothermic, temperature increased. Is that right? If the reaction is endothermic, there will be a drop in temperature. In other words, in chemistry, we always measure heat change. However, during the measurement, we can carry out at constant volume. Now, underline, if a chemical reaction is carried out at constant volume, that means volume doesn't change. Now, what does it mean? Let's look at this photo. Here we have a flask, and in the flask there is a reaction. Magnesium rubrum react with hydrochloric acid. Now let's focus on the stopper. Okay? Because the stopper is present, in other words, this reaction occurs at constant volume. The total volume doesn't change. If under this condition we are measuring the heat change, look at this sentence. The heat change measured is called the change in internal energy of the reaction. Now I repeat, if a chemical reaction is carried out at constant volume, you may imagine there is a stopper at the mouth of the flask, so that the volume doesn't change. The heat change measured is called the change in internal energy of the reaction. You may ask, what is the meaning of internal energy? Now, let's look at the learning tips. The internal energy of a substance is the sum of the total kinetic energy and potential energy of all particles in that substance. For physics students, I think you have no problem about these terms. Kinetic energy is about velocity, okay? Potential energy, it is a method of height. But for chemistry students, it doesn't matter. You have learned these two terms in Form 1 IS, kinetic energy and potential energy. The summation of the total kinetic energy and potential energy is called the internal energy. Bear in mind, okay? Now, however, if a reaction is carried out at constant pressure, the heat change measured is called enthalpy change of the reaction. Now let's compare what is the meaning of this sentence. A chemical reaction is carried out at constant pressure. Now let's turn to the next page. Let's look at this photo. It can help you a lot to understand. Here we have a flask without a stopper, okay? And inside the flask we have the reactants. Magnesium rubrum reacts with dilute hydrochloric acid. Can you tell me what are the products? Magnesium reacts with hydrochloric acid to form hydrogen gas and magnesium chloride. Do you remember? Bear in mind, you need to balance the equation. Now, because hydrogen gas is formed, okay, pressure inside the flask is building up, okay. However, because it is in an open system, that means you can imagine there is a weightless piston. As hydrogen gas is produced, it will push this weightless piston up and up and up, so that the pressure inside the flask remains constant. While you are pushing up the weightless piston, actually you are doing work. Work done against atmospheric pressure. Highlight this sentence. Work done against atmospheric pressure. Work done, you may consider it is the force times distance, okay? Doing work against the atmospheric pressure. Under this condition, if you are measuring the temperature change, it is called the enthalpy change. Enthalpy change. Now, it is quite difficult to understand, particularly for those who haven't studied physics. Now, please turn back to page 5. Let's repeat by using this example. Magnesium reacts with hydrochloric acid. Magnesium chloride and hydrogen gas are produced. Okay? If the experiment is carried out in a closed system, that means stoppered flask, okay, the volume remains constant. The heat change at constant volume is the change in the internal energy. Now, in other words, look at this sentence. Heat change at constant volume is equal to the change in internal energy. You may consider it is negative 433.8 kilojoule. What does it mean? 433.8 kilojoule of heat is given out for every mole of magnesium reacted. When 1 mole of magnesium is reacted, it will give out 433.8 kilojoule. Okay? Turn to the next page. However, if the same reaction is carried out in an open system, that means without a stopper, the pressure remains constant, okay? Only 430.8 kilojoule of heat is given out. That means less heat is given out. Why? Because some of the energy is used to do work against the atmospheric pressure. This is because hydrogen gas produced from the reaction has to push back the air in the atmosphere. Thus, doing work, energy is needed, and consuming energy, which is approximately 3.0 kilojoule in this situation. So let's look at this equation. Heat change at constant pressure is equal to the change in internal energy together with work done on the surroundings, because work has to be done, okay, in this example. Under this condition, we have another term, which is called enthalpy change. Now I repeat, enthalpy change of the reaction is the heat change at constant pressure. Enthalpy change of the reaction is the heat change at constant pressure. Understand?
This video is about enthalpy and enthalpy change, or delta H. If you look up enthalpy, there's a couple of different definitions for it. One calls it the heat content of a substance. Having a high heat content doesn't necessarily mean it's hot. Produce heat. Another definition is the total kinetic and potential energy of a substance at constant pressure. In this course, we can think of enthalpy mainly as chemical potential or stored energy. For example, gasoline has a high enthalpy. It's got a lot of stored chemical potential, whereas water does not have a very high enthalpy. Chemists are interested mainly in the enthalpy change, or delta H, during a chemical reaction. Let's consider an exothermic reaction. This is one that releases heat to the surroundings. Here's a graph of enthalpy versus the progress of the reaction. This is the beginning of the reaction where you have the reactants, and this is the end of the reaction where you have the products. For this exothermic reaction, as the reaction proceeds, you notice that the enthalpy goes down. So we say that delta H is negative. So what happens to this enthalpy? Well, what happens is it's converted into heat. So as it's losing enthalpy, it's producing heat, and this heat is released to the surroundings. So the surroundings would get warmer or cooler. You guessed it, they would get warmer. Okay, this time we're going to look at an endothermic reaction. Remember, an endothermic reaction absorbs heat from the surroundings. Here's a graph of an endothermic reaction. Notice that the reactants gain enthalpy as they form products. So enthalpy goes up. We say delta H is positive. Where does this enthalpy come from? Well, where it comes from is heat is absorbed from the surroundings, and the reaction changes heat into stored energy, or enthalpy. So the products have more stored energy, or enthalpy, than the reactants. So what do you think will happen to the temperature of the surroundings? They'll get cooler because the surroundings are losing heat. It's being converted to enthalpy by the reaction. Let's have a look and see how enthalpy and heat are dealt with in chemical equations. In one type of equation, the delta H is written beside the equation. It's not really part of the equation. There's no plus sign or anything between them. The delta H is just beside the equation. If delta H is negative, it means enthalpy is going down, and this is an exothermic reaction. So delta H negative means it's exothermic. Here's a reaction here. Again, the delta H is beside the equation, and this time it's positive. So if delta H is positive, it means it's an endothermic reaction. Another way of showing heat is through a thermochemical equation. Thermo means heat. In these types of equations, the heat term is right in the equation. There's no delta H shown. The heat term could either be on the left side of the arrow or the right side of the arrow. If the heat term is on the left side of the arrow, this is an endothermic reaction because it's using up heat like a reactant. Here's an example. This is the heat term, and it's on the left side of the arrow. So this is an endothermic reaction. If the heat term is on the right side of the arrow, then it's exothermic. This gives off heat like a product. So here's a reaction here with the heat term on the right side. Notice there's no delta H shown here. So if the heat term is on the right side, that's an exothermic reaction. Here's a question for you here. When methane, or CH4, is burned in oxygen, carbon dioxide and water are formed, and 802.3 kilojoules of heat are released to the surroundings per mole of methane. So, looking at these choices, which of the following correctly represents this reaction? So I want you to look at these, try and figure out the answer or answers, and then you can turn the video back on and check your answers. So here's the answer here. Since heat is released, number 2 is correct because the heat term is on the right side of the arrow. Answer number 4 is also correct because here the delta H is shown, and since this is an exothermic reaction, it's releasing heat, delta H is negative.
Now, let's move on to the next part. It's about enthalpy and enthalpy change. All substances have a certain enthalpy, okay? Which is an indication of energy content. And do you remember what is the meaning of energy content? It is the total sum of the kinetic energy and the potential, chemical potential energy of a substance. In fact, the enthalpy of a substance cannot be measured directly, okay? Instead, enthalpy change is measured, okay? That means this sentence, the enthalpy change, we're talking about change between reactants and products can be measured experimentally. So, let's look at the symbol. Enthalpy, sometimes called heat content, or is the heat change at constant. Do you remember what is it? Is the heat change at constant volume or pressure? Constant pressure. Bear in mind. Okay? Is denoted by the symbol H, capital letter H. If we are talking about enthalpy change, we'll add a delta before H. Delta means change in enthalpy. By definition, enthalpy change of a reaction, delta H, is equal to the enthalpy of products minus enthalpy of reactants. Product minus reactant. Understand? So, by using the video, if delta H is positive, what does it mean? Heat is taken in or is absorbed from the surrounding. A positive value of delta H, now bear in mind, delta H is equal to the enthalpy of product minus enthalpy of reactant. If we have a positive value of delta H, it indicates that heat is taken in or absorbed from the surrounding. What does it mean? It means that it is an endothermic reaction. An endothermic reaction. On the contrary, if delta H has a negative value, negative, that means the heat content of the product is smaller than the heat content of the reactant. Heat is given out or is released to the surrounding. In other words, the reaction is exothermic. Understand? So, let's have a short summary. First of all, you must be able to tell me what is the meaning of enthalpy change. Do you remember what is an enthalpy change? An enthalpy change of a reaction is the heat change at constant pressure. This is the first point of our summary. Okay? What is the meaning of constant pressure? That means we carry out the reaction without a stopper. Second, what is the meaning of delta H, enthalpy change, which is the enthalpy of product minus the enthalpy of reactants. Third, if the delta H has a positive value, what does it mean? It means that the reaction is endothermic. On the contrary, if the delta H has a negative value, what does it mean? It means that the reaction is exothermic. Now, let's try class practice 33.2. For the following reaction, hydrogen reacts with chlorine to form hydrogen chloride. A student suggested that the heat change for the reaction measured at constant pressure, underline, measured at constant pressure, is the same as the change in internal energy. Change in internal energy of the reaction. Do you agree? Oh, I give you maybe 5 minutes to think of the answer. You may pause the video. After that, you may turn on the video again, okay, to see whether your answer is correct or not. Oh, let's see. This is the reaction. Hydrogen reacts with chlorine to form hydrogen chloride. Now, let's pay attention to their states: gas, gas, and gas. Now, in the reactant side, we have 1 mole of hydrogen react with 1 mole of chlorine. That means altogether there are 2 moles. And then on the product side, there are 2 moles of hydrogen chloride. In other words, during this reaction, there is no change in the total volume, gas volume, before and after the reaction, as there is no change in the total number of moles of molecules, of gaseous molecule. Total number of moles of molecules. As I mentioned before, there are 2 moles altogether. There are 2 moles of molecules on the reactant side, and there are 2 moles of gaseous molecule on the product side. Look at this sentence again. As there is no change in the total number of mole of the gaseous molecule in the reaction. Therefore, there is no change in the total gas volume. No change in the gas volume. Next, let's write down this sentence again, these definitions again. Enthalpy change. Do you remember what is it? Enthalpy change happens at constant pressure, is equal to the change in internal energy plus work done on the surrounding. This is the definition. Okay, and do you remember how to do well? Look at these photos again, these diagrams again. During the reaction, there is a change in gas volume because hydrogen gas is produced. As hydrogen gas is produced, hydrogen gas need to do work against the atmospheric pressure. In this situation, there is a change in the number of mole of gaseous molecule, which is the hydrogen gas, the only gaseous product, hydrogen gas. As there is a change in the volume, so we have to do work against the atmospheric pressure. Let's move back to this situation. As there is no change in the total number of mole of gaseous molecules on both sides, so there is no change in total gas volume. Because there is no change in gas volume, so there is no work done. There is no work done on the surrounding. In other words, in this situation, maybe let's complete. There is no work done on the surrounding. Okay, there is no work done on the surrounding. So let's move on. Let's go back to this equation. As work done is equal to 0 in this situation, therefore enthalpy change at constant pressure is equal to the change in internal energy. It's true. Do you agree? So agree. It's difficult. Again, if for physics students, if you have stuck these topics, is about pressure, okay, you may understand this idea in detail. But for chemistry student, it doesn't matter. Seldom asked in the examination about class practice 33.2.